Welcome to qnawire.
Hi, so for this problem what we're going to do is to find out the equations of motion for this system. I'm going to use, instead of using phi, I'm going to use the angle theta because I'm more used to label things like that. So in order to get the Lagrangian, the first thing that we need to get is the kinetic energy operator. That is going to be 1/2 of the mass times the velocity of the variable x, that is the velocity that I'm going to get in the axis of the spring, plus L plus x, that is going to be a radius squared, times the angular velocity that is going to be generated on my system. At the same time, I also going to have the potential that is going to depend on x and my angle theta. That is going to be given by mg L plus x cosine of theta plus 1/2 of kx squared. With this, my Lagrangian, which is defined as t minus b, is going to become 1/2 of mass x dot squared plus L plus x squared theta dot squared plus mg L plus x cosine of theta minus 1/2 of kx squared. So this is my Lagrangian for the system. Next up, we need to identify the fact that this Lagrangian depends on two different equations. Sorry, on two different variables. So my Euler-Lagrange equations are going to depend on x dot and on theta dot. So I'm going to have two different sets of equations. The first one, with respect to x, the Lagrangian with respect to x over here, yields the following equation, which you can verify. Mx double dot, it's going to be m times L plus x theta dot squared plus mg cosine of theta minus kx. If we want to identify this using Newton's second law, remember that this is force equals mass times acceleration. This is nothing but the radial force that we're going to get, complete with the centripetal acceleration given by this component over here. So that would be the interpretation with respect to Newton's law of this first equation. Next up, we need to get the Euler-Lagrange equation for the theta variable, for the angle. From here, what we are going to get is derivative with respect to time of, this is simplify a little bit, L plus x squared theta dot, and this is going to be equal to minus mg L plus x sine of theta. Next up, we can apply chain rule directly here, s plus x squared theta double dot plus 2 times mass times L plus x dot theta dot, and this is going to be equal to the same thing, minus mg L plus x sine of theta. Here, realize that we have L plus x multiplying on both sides, so we can simplify this a little bit, and we're going to get m times L plus x theta double dot plus 2 times m x dot theta dot equal minus mg sine of theta. So these are both of the equations that we're going to be working with. The first one and the second one. Let me put this in red just to make things a little bit more clear. And finally, how can we interpret this equation? We can look this part, and you can realize that essentially the torque is going to be equal to the rate of change of the angular momentum that we have in our system. So those are the interpretations using Newton's second law. So next up, the problem asks you to use the approximation that we are going to consider small oscillations of the spring, labeling the equilibrium position as the length plus an epsilon, right? This is the same as saying that x is epsilon for this case. The same thing is true for the angles, right? That we're going to have a small angle approximation, so the value for theta, it is going to be small, and the first derivatives are going to disappear. So using this approximation, the first thing that we can realize is that this term is going to die out. Next thing that is going to happen over here, the other thing that we can simplify a little bit is that, remember that within this small angle approximation, sine of theta is going to be equal to theta, and cosine of theta is going to be equal to 1. So the two equations that we have, let's rewrite them and expand them a little bit. We have mx double dot for equation 1. This is going to be equal to, I'm going to expand all of the parentheses. We are going to get ml theta dot plus mx theta dot squared in both of them plus mg cosine of theta, but we said that cosine is equal to 1, so plus mg minus kx. For the second equation, we have ml theta double dot plus mx theta double dot equal to minus mg theta. So we're going to get rid of all of the things that have a product in between lengths and theta. So ml theta double dot, mx times theta double dot, x is very small, so this goes to 0. The second equation is already fully decoupled. In the first one, we have mx theta dot squared, and here we're going to have the change, and also we are going to have here a product of L times theta dot squared, which is also going to go to 0 under this small angle approximation. With this, we have the fully decoupled equations, which is mx double dot is equal to mg minus kx, and ml double dot theta double dot is equal to minus mg theta. And these are the final equations of motion that we get. And that would be all. Here, just a small comment. In this case, the L times theta double dot, remember they do not cancel because this is just the second derivative. It's not a product of the second derivative by itself, right? In the first case, yes, we have a product of theta dot times theta dot, so that is going to go to 0. And that would be all. Thank you very much.